apparently you're interested in time, so it seemed appropriate to talk about going to the beginning of time. And I want to talk about the efforts we've made to go back and to the earliest moments of the Big Bang. And we are on the threshold of potentially a revolution in that regard. So that's what I want to talk about, and I hope my remote will work. That's the one thing we haven't checked before, which I will now. Usually it requires two or three times before. There we go. Okay, this is the universe we live in. This is the most recent Hubble Space Telescope picture, the multi-chromatic image, which means the colors are real. Every image in this, every dot in this image is a galaxy except for that one. So there are 100 billion galaxies in the observable universe, approximately, each containing 100 billion stars. And and in this case, the faint blue galaxies are the darkest, are the most distant galaxies. So the most distant galaxies in this image go back to maybe about 10 billion light years away. So we go back 10 billion light years into a universe that's 13.8 billion years old. So it takes us some of the ways back, and with the successor to the Hubble Space Telescope, the James Webb Space Telescope, will go back to the earliest star formation, the first light in the universe, which probably happened between a few 100 million years and 1 billion years after the Big Bang. But with light, with visible light, that's as far as we can go back. When you look at this image, by the way, the fact that there are many galaxies is interesting. You might ask, where is this picture taken, which direction? And it doesn't really matter, because the universe is the same in all directions, roughly the same number of galaxies and the same in all directions. That is a surprise because of time, in a sense. Because if you look at light from the most distant end of the universe in that direction, then now is the first time in the history of the universe that those regions can communicate causally, since no signal can travel faster than light. So if now's the first time that they could causally communicate, the question is, how do they know to be exactly the same? That's been a puzzle that has driven much of the theory in trying to understand the early universe. Why is the universe the same in all directions? And we'll come back to that, perhaps, because we have an explanation that we can test. But with visible light, this is as far back as we can go. We can go back further, and the farthest we can go with electromagnetic radiation is the cosmic microwave background radiation. When the universe was about 300,000 years old, it became transparent to visible light, essentially, or to electromagnetic radiation. Because before that, before the time of 300,000 years, the temperature of the universe was greater than 3,000 degrees Kelvin. And when the temperature was higher than that, then basically hydrogen would be dissociated into protons and electrons. And you'd have a plasma. And a plasma is opaque to radiation. So the universe was opaque to electromagnetic radiation, and then when it cooled below 3,000 degrees, hydrogen combined became neutral, and the neutral matter became transparent. So we can, just as my laser can go out as far as that wall, when we look out, we can see back to a wall, essentially, the moment when the universe became transparent, and the radiation that was emitted from that surface we call the cosmic microwave background, because that radiation, which was a temperature of 3,000 degrees, has now cooled to a temperature of 3 degrees approximately, and that radiation is in the microwave band. It was discovered by accident in 1965 by two people who didn't know what they were doing, but they won the Nobel Prize anyway. You don't have to know what you're doing to win the Nobel Prize, you just have to do it. Anyway, this is an image of that cosmic microwave background. And it has false colors. The colors represent temperature. So you can see that it's hotter in some spots and colder in some spots. Therefore, it certainly doesn't look completely uniform across the entire sky. Now, before I explain that, let me just explain this is a projection of that surface at 300,000 light years. It's essentially the same projection as we would have projecting the surface of the Earth, although that's upside down. There we go. My wife is from Australia, so I try not to be Northern Hemisphere centric. And so the projection I just gave is this one here is the same. So this is up and that's down, looking at the sky. This is where our galaxy is, the plane of the galaxy. So this is just pollution in between us and that microwave background surface 300,000 light years after the Big Bang. This is a baby picture of the universe. At least 2 Nobel Prizes have been given for it. Because this radiation, the light that's observed from, in this case, came from the universe when it was 300,000 years old, well before any structure, any stars had formed. And you see that there are primordial lumps. There's hot spots and cold spots. Now, as I say, the variation here is somewhat an illusion because it's extremely uniform. The hot spots are roughly 1/100,000th of a degree hotter than the cold spots. So this is, the universe is uniform at that time in temperature to almost 1 part in 100,000. That uniformity is again striking and unexpected in some sense, because there's no within the context of the standard Big Bang picture, though it shouldn't be uniform, because this region here could never have communicated with that region there. Yet to 1 part in 100,000, they're uniform. Now, as I say, this is the pollution from our galaxy, and by measuring this over different frequencies, this radiation it looks like a black body. The radiation emitted from the galaxy doesn't, and by comparing the two, you can try and get rid of the galaxy. This is the best current picture taken with a satellite called the Planck satellite, and launched by Europe, in fact, and where the galaxy has been removed. So this is the best baby picture we have of the universe. And you can see the hot spots and the cold spots. The question is, first of all, why is it so uniform? And secondly, what created the small lumps? Because without these hot spots and cold spots, the hot spots and cold spots represent regions where there's a little more matter and a little less matter than average. Without that, there'd be no structure in the universe today. If the universe were exactly uniform, then there'd be nothing around. But the regions actually, in this case, the cold spots, represent regions where there was a little excess of matter, and that matter would collapse to form all the stars and galaxies and aliens and everything else in the universe. So that these would later on to form basically all the structure that I showed you in that other picture. And we have an understanding potentially how that can happen. In fact, it requires lots of exotic physics, including dark matter and dark energy, which I won't talk about, but I'll be happy to answer questions about. But this is as far back as we can see, 300,000 years after the Big Bang, which is not bad, but we'd like to get back earlier. But this is as far back as we'll ever be able to see in electromagnetic radiation because of that wall. Because at earlier times, there's no way electromagnetic radiation can propagate through that dense plasma that was the early universe. If we want to look back to earlier times, we have to look for a signal that can propagate from the earlier times to today. And that means we have to look at some sort of radiation that is less strongly coupled to matter than electromagnetism. Okay? And of course, what we use is gravity, because gravity is by far the weakest force in nature. And we use a signal from gravity that was first predicted by Einstein in 1916, which is the fact that because, of course, general relativity tells us that space and time depend upon the nature of matter and energy within the universe. That relationship, the fact that matter and energy determines the nature of space and time, which then determine the evolution of matter and energy, that nonlinear relationship is what makes general relativity more complicated than Newtonian gravity. But because matter and radiation affect the properties of space, every time I do this, I'm curving space around me in a time-dependent way. All of us curve space around us. But when I curve space in a time-dependent way, I produce a disturbance. And it's essentially the same as the disturbance that Maxwell first wrote down when I shake an electric charge. I produce an electromagnetic wave. I produce a disturbance in electric and magnetic fields. When I move a piece of matter around, I produce a disturbance in space and time, in the fabric of space and time, and it propagates out at the speed of light. And we call that a gravitational wave. Einstein called it a gravitational wave. He actually predicted it in 1916. In 1936, he wrote a paper saying he was wrong. He submitted it for publication. He'd moved to the United States at that time. He submitted it to an American physical journal. And it was rejected because it was wrong, actually. He was very upset. He wrote to the editor saying, turns out in Germany he'd never been subjected to refereeing before. And he wrote to the editor saying, I sent this for publication, not to be refereed. And you should try that. Anyway, but happily, it turns out that the error was discovered. He discovered the error again before it was published, so that erroneous paper never appeared. But eventually, that prediction came true. And in fact, the gravitational waves do this. If this is a gravitational wave coming out of the screen, then what it represents the fact is that when there are many gravitational waves moving throughout this room right now, and as they move throughout the room, the distance between the walls gets a little bit shorter, and the distance between the floor and the ceiling gets a little bit longer, and it oscillates back and forth. And these are occurring right now all the time, but gravity is so weak, when I do this, I produce a gravitational wave. But the gravitational wave is so weak that we will never measure that. It is a challenge to measure gravitational waves. This is the two-dimensional version. This is the three-dimensional version of three-dimensional animations have no information, but they look good. Anyway, so this is meant to hypnotize you, I think, as I talk. The question is, can we measure these? And it is truly amazing that anyone ever thought we'd be able to measure these. Because while we'll never measure gravitational waves from my hand moving, we can look for more extreme phenomena, cataclysmic events in our universe, because the intensity, the amplitude of the gravitational waves will depend directly both on the amount of mass and how quickly it's moving. Those two factors will determine whether you'll have an observable gravitational wave. And the most cataclysmic events we can think of in the universe are the collision of black holes. Large solar mass black holes, if they exist, would produce an abundance of gravitational waves that you might hope to measure. And so a brave set of experimentalists over 50 years, 40 years, assembled what is now the largest gravitational wave observatory in the world. This is the one part of it. This is the LIGO, the Laser Interferometric Gravitational Wave Observatory. This is Hanford, Washington. There's an identical version of this in Livingston, Louisiana. And what it consists of, it's an interferometer. It consists of two perpendicular tunnels, each 4 kilometers long. And one wants to measure and very simply, if a gravitational wave comes down from above, the length of this tunnel will get shorter, and this one will get longer, and then this one will get shorter, and that one will get longer. So it's very simple. You just measure the length of the tunnels. It's not so simple, of course. What you do is you hang a mirror here, and we use lasers. We use interferometry, as I'll show you in a second. And we reflect light back and forth to try and determine the length of those tunnels. But the challenge is worth noting, and this is the reason I'm happy I'm a theorist, not an experimentalist. If two solar mass black holes were to collide in a nearby galaxy, producing the most intense gravitational waves you can expect being produced in our universe today, then we can calculate how much this length will change. And this, by the way, is a time measurement too, so it's relevant. We can calculate that if such an event happened, the length of this 4-kilometer long tunnel compared to this 4-kilometer long tunnel would change by an amount equal to 1/1000th the size of a proton. And that's the challenge, to measure a 4-kilometer long tunnel to an accuracy of 1/1000th the size of a proton. This requires the most advanced optical technology you can imagine. Because well, I'll talk about quantum mechanical vibrations later in a different context, but even if you're reflecting light off the surface of a mirror, even the quantum mechanical vibrations in the mirror generally exceed that. So we have to use squeezing. We have to use sophisticated quantum optics that basically cause the quantum fluctuations in the mirror to be in this direction and not that direction. One of many, many bits. And we send incredibly intense lasers with a very high vacuum and bounce them many times off one another. And schematically, this is what one does, which is what one does in interferometry. One has a mirror, and one basically separates the light rays into two, and one looks for interference here. And one very carefully arranges things so that it's a null, so that these the waves, when they reflect, come back out of phase, and so there's no signal on the mirror, and we see darkness. So they're exactly out of phase. And then with small changes in this length, one can look for a signal on the mirror that basically gets brighter and darker. That's the idea. Okay. Now, you can imagine that this is a challenge because of the fact that we're looking for a variation in an amount equal to 1/1000th the size of a proton. There are many things that cause vibrations in this system. If a truck hits a pothole 20 miles away from this machine, it will cause a vibration that will exceed the signal you're looking for. So there's lots of background, and that's one of the reasons why we have two detectors. Because if a gravitational wave comes by Hanford, Washington, one could calculate it takes 8 milliseconds for it to pass through the Earth to get to Livingston, Louisiana. So we look for signals that are identical, and of course we have to have very good time resolution. We look for signals that are identical in Livingston, Louisiana and Hanford, Washington, but separated by 8 milliseconds. But even that is not the only way we can do this. Now, we need more than that. Now, this detector was originally built in 2000, and it had only the resolution of 1/100th the size of a proton. It was operated because who knew? Maybe there were bigger events than we expected. Nothing was seen. The detector was upgraded over a course of 15 years. And on September 14th in 2015, it went online with a resolution precision of 1/1000th the size of a proton. And Ray Weiss, who was involved in the original proposal, said that there should be an engineering run. No data should be taken as the machine was tuned up, which is what you do. I'm sure those of you who do frequency standards do a tuning period before you actually take measurements. Happily, the graduate students didn't listen. So the machine was turned on, and 1 hour later, a signal was observed, an unambiguous signal of gravitational wave. The first observation of gravitational waves in history. Now, here are the observations. Now, before I go into them, just having the experimental technology is not good enough because there's still lots of background. You have to know what the signal is you're looking for. If you didn't know what the signal you were looking for, there's no way you'd be able to extract the signal from background. And while the experimental technology was not available till 2015, the theoretical technology was also not available till the early parts of the century. Because when two black holes collide, you're in a region of very strong gravity. And the calculations are extremely, the space itself is bending and boiling and bubbling like a turbulent sea. And it required new methodology, theoretical technology, to calculate what the gravitational wave signal would be, and it required supercomputers. That was all put together, and being able to interpret, do time intervals, basically, and understand what time was in the context of general relativity. All that came together also at the same time. And those two things came together, so this was the first time in human history that we could have possibly even measured a gravitational wave, and it's amazing that within 1 hour of putting all those things together, one kindly occurred that was measurable. Here is the signal in Hanford. Here's a signal 8 milliseconds later in Livingston, Louisiana. The two superimposing each other identical. And you can see this somewhat smoother curve is the prediction if two black holes, one 36 times the mass of the sun, one 29 times the mass of the sun, collided and coalesced in a galaxy 1.3 billion light years away. So it's kind of amazing that this coalescence occurred 1.3 billion years ago, and if they'd waited an hour to turn on the detector, would have missed it. It's incredible. It's an amazing story in that sense. So this is a platinum signal. We have detected gravitational waves. Now, what happens when these gravitational waves come in? It's as interesting and as daunting as the detector technology is. The observation itself is remarkable. I'm going to show you a video of this is an artist rendering, clearly, of what it would look like. Here are the two black holes. They're bending space around them, so you can see the light is distorted around them, and it's slowed down. These two black holes, in the last moments of their life, are orbiting each other at 200 times a second. So they're 30 times the mass of the sun, orbiting each other 200 times a second. Okay, that alone is amazing. In any case, you can see what happens as they move around. This is slowed down. This is the last 0.2 of a second in the life of these two black holes. You'll see them as they coalesce. Here, obviously, they're distorting space around them. As they coalesce, at the moment they collide, you'll see the gravitational wave signal. You'll see space jitter. So look for that. There it is. It's shaped. Okay? That was the effect that later on, 1.3 billion years later, was seen here. Now, this is an amazing thing, because in that so we have a 36 solar mass black hole colliding with a 29 solar mass black hole. So what size is the black hole they form? This is an advanced audience. You should be able to work this out. 36 solar mass black hole plus 29. Well, we would think it would be 65. I'm not going to pick on anybody, but it's actually wrong. It's a 62 solar mass black hole. That means 3 times the mass of the sun. 3 times the mass of the sun is converted to gravitational waves in 0.2 of a second. Now, to put that in perspective, the sun burns 100 billion hydrogen bombs every second. Over its 10 billion year lifetime, will convert less than 1% of the mass of the sun into energy, still enough to power our civilization and everything else. So for 10 billion years, 100 billion hydrogen bombs every second, 1% of the mass of the sun. In 0.2 of a second, this collision converted 3 times the mass of the sun into energy. That means during that 0.2 of a second, more energy was emitted in that system than is emitted by all the stars in the visible universe. And more energy is emitted into gravitational waves in 0.2 of a second than is emitted into light by all the stars during that same time in the visible universe. It's amazing to think of the violence of that event, but at the same time, it was completely invisible, and it would have been invisible if we hadn't developed the technology to look for it. And we now have opened a new window on the universe. This is a new form of astronomy. It will be the new astronomy of the 21st and 22nd centuries. We're living at a time that, in that sense, that's akin to the time when Galileo first turned his telescope and saw the moons of Jupiter, opening a new window of visible astronomy. And we've heard about various people who've used that in many important ways in understanding our universe. This will reveal mysteries and aspects of the universe that are otherwise hidden, and it is amazing. But in fact, it's not the kind of gravitational waves I want to focus on. It's one kind. The discovery is remarkable, and it will win a Nobel Prize this October, I expect. But there's another source of gravitational waves that's more interesting, and those come from literally the beginning of time. And we have another kind of detector to look for them too. This is one of the detectors. This is at the South Pole. This is the BICEP detector at the South Pole. It looks at the cosmic microwave background radiation, which I told you comes from the time when the universe was 300,000 years old. But in fact, there's an imprint, there's a signal we think is imprinted in that radiation that comes from a much earlier time. A time when the universe was a millionth of a billionth of a billionth of a billionth of a second old. A millionth of a billionth of a billionth of a billionth of a second old. If we can see that signal, we will observe what the universe was like when it was a millionth of a billionth of a billionth of a billionth of a second, which is a time, I think, that's shorter than any of the times that have otherwise been considered at this meeting, probably. Okay. Now, this detector, in order to do this, we have to use sophisticated technology because the imprint in the microwave background is very small. So, in fact, the South Pole is not cold enough. we have to send liquid helium down there, which we do only in the summer. I was amazed when I first learned this about 20 years ago. Maybe you know this, but we can't send aircraft down to the South Pole in the wintertime. We can go to the moon. Well, that was faked, but we can no. And we can go to the deep ocean. We can go, but we can't go to the South Pole, so we send it in the summertime. That's why this particular picture that I'm going to show you is one of my favorites. It's a picture taken from the BICEP telescope at sunset in the South Pole. Now, sunset in the South Pole happens once a year. So, but because we can't send aircraft down there, if you're taking this picture, you're there for the winter, which is why it was taken by a graduate student. Okay. Okay, so what signal are we looking for? Well, now I don't want to make this just a qualitative talk, so I want to talk a little bit of physics and introduce you to a little bit of quantum field theory, which is the theory we need to describe the early universe. The current idea is that in the early history of the universe, when it was a millionth of a billionth of a billionth of a billionth of a second old, the universe underwent a rapid expansion, increasing in size, in volume, by a factor of at least 10 to the 90th in a millionth of a billionth of a billionth of a billionth of a second, due to the fact there was an energy stored in space. If you put energy in empty space, it's gravitationally repulsive, and it caused the universe to expand very fast, and that energy eventually was released. That's this theory called inflation, and I'll talk a little bit about it later, why we think it happened. But it produced, the wonderful thing about this theory is it explains the two questions that I gave you earlier. Why does the universe look the same in all directions? And why are there small lumps? Where did they come from? Who created them? Certainly not God. Physics. Okay? Now, the first answer is quite easy to the first question. Why is the universe the same in all directions? If the universe expanded by a huge amount in a short time, then regions which would otherwise, now when we look at the universe, we think that this is the first time they're causally connected. But if at early times the universe was much smaller than we would have otherwise thought, those regions were in causal contact. And before inflation happened, they could thermalize, and the universe could become the same in temperature. So there was enough time for the temperature to become uniform. So inflation would, in some sense, predict why the universe is the same. It would predict the universe looks the same in all directions, because what would happen then is the universe would expand out very, very fast and get frozen in that situation until that energy was released, and we'd cause a hot Big Bang. But that Big Bang would be uniform. So one of the first predictions of inflation is the universe should be uniform in all directions. Great. But it goes beyond that. It predicts small lumps, and it's amazing that those small lumps are due to quantum mechanics. At the forefront of physics today is in some sense quantum engineering, is trying to look for macroscopic manifestations of quantum mechanics, be it by quantum computing or quantum teleportation. And so using quantum mechanics over macroscopic scales is kind of one of the forefronts of the technical aspects of physics. But in fact, we're all manifestations of this. As I look out at the lumps in this room, we're all macroscopic quantum mechanics, because inflation says that those lumps that later created the galaxies and clusters and eventually stars and planets and people came by quantum mechanics. And I want to explain to you how that happens. So we have this period. Inflation, we think, happened when the universe was very early, at 10 to the minus 35 seconds. And it underwent this rapid period of expansion. And as I say, that's why it explains things, because the standard model, the universe would have been at this time, the universe would have been the size of a soccer ball. But if inflation happened before that time, the universe would be the size of an atom. And there would have been enough time for things to thermalize over what is now our observable universe. But a rapid expansion of an entire universe is a far more cataclysmic event than the collision of two black holes. Moving the mass of our entire universe rapidly, expanding it, will produce gravitational waves. And I want to show you how. But first I want to tell you this miracle of how quantum mechanical fluctuations became us. And it's a little technical, but not too technical. So inflation happens because there's a phase transition in the early universe. when water is supercooled and turns to ice, that's a phase transition. Okay, it's a metastable state. Water below 32 degrees on the roads in the wintertime, getting stirred up by cars, remains water until the evening when the cars don't go by, and suddenly it freezes, forming black ice, and you have accidents. That a phase transition in physics can be thought of as by something called an order parameter. Some parameter gets stuck in some metastable state and eventually goes down to the minimum of potential, and that produces a phase transition. Okay? Now, in physics, we think there's a field. We can imagine fields, quantum fields, that get stuck in some metastable state. And when they get stuck in some metastable state, they store energy. And that energy density is, as I say, will cause the universe to expand exponentially. Because if you store energy in empty space, it's gravitationally repulsive, not attractive. So some field in the early history of the universe, as it was cooling down, got stuck. And if it remained stuck, we'd still be expanding exponentially, and there'd be nothing left in the universe, and the universe expansion would be so fast that nothing would have happened. Eventually, in some region, the transition happened, and that energy that was stored in empty space gets turned into, after that field goes to its new minimum, gets turned into the energy of radiation and matter, and you have a hot Big Bang. So this is a transition that's the end of inflation, turning all of that energy of empty space to the energy of everything we see. Now, what can cause that transition? Well, this is a quantum field theory, and quantum mechanics always has fluctuations. So that field is not still, it's fluctuating due to quantum mechanics. And it turns out that the scale of those fluctuations is determined by the energy stored in the field. It's the only dimensional parameter around in the problem. So the scale of all fluctuations have to have a scale determined by the only dimensional parameter in the problem, which is the energy stored in the field. And so we can say that this field, the expectation value of the fluctuations in this field, is proportional to that parameter. It's called the Hubble constant. It's related to the energy density stored in that field. That's simple. Okay? Now, if you have a perfectly flat potential, the only thing that's going to cause that field to move is quantum fluctuations. Okay? If, however, you have a potential that's strong, that has a strong curvature there, a big slope, then in addition to the quantum fluctuations, there'll be a classical rolling down of the field. Now, what causes the density fluctuations we see in the universe today? What happens is that due to quantum fluctuations, one region in the universe leaves inflation before another region. And when things are inflating, the energy density is constant. It doesn't change. Once you've left inflation and you produce matter and radiation, then the energy density changes as the universe expands. The energy of nothing doesn't change. The energy of something gets diluted as the universe expands. So the region that leaves inflation a little bit before another region will have a little bit smaller energy density today, because that radiation will have redshifted. It'll have gotten smaller. Now, if there were quantum fluctuations and nothing else, then if they occur very randomly, then, well, the density fluctuations would be huge, because one region would leave inflation a lot longer than another, a lot earlier than another region. If there's a huge slope to this potential, then all regions of the universe are leaving inflation at the same time, and some regions will leave a little bit earlier than other regions. So if you work that out, the density fluctuations we see in the universe today will depend upon two things: the slope of that potential and the energy density in the potential. If the slope were 0, the density fluctuations would essentially be infinite, because one region would leave inflation infinitely before another region, essentially. If the slope is very large, then the density fluctuations are very small, because all regions leave inflation at the same time. This is a prediction of inflation. It will produce a uniform, basically a Gaussian distribution of density fluctuations, independent of frequency, independent of wavelength, and dependent upon only these two parameters. And so it will produce a scale-independent spectrum of fluctuations. And that's precisely what we see in the cosmic microwave background today: a scale-independent spectrum of fluctuations. So what that really means is that quantum mechanical fluctuations produce everything we see. We are a manifestation of macroscopic quantum mechanics. And that's remarkable. Now, you might say, since that agrees with the observations we make, we know inflation happened. We can't say that. Because inflation is an idea, not a theory. And it can depend upon the details of how this happens. And it turns out that if you change those details, you could agree with the predictions of almost anything we see. So a theory that can't be falsified is not a theory necessarily. And so there's strong circumstantial evidence, we think, that the simplest theory of inflation, I should say, produces exactly what we see. With fancy versions of inflation, you can produce other things. Since what we see is consistent with the simplest version of inflation, it gives us great confidence that inflation happened. But there's a way to look for an unambiguous signal of inflation, something I've been interested in for 30 years. And that is, inflation doesn't just produce these density fluctuations, it produces gravitational waves. And it produces them by the same kind of mechanism. If gravity is a quantum theory, then there must be fluctuations in space and time, as well as fluctuations in quantum fields. And it turns out that if you look at gravitational waves, they come in two helicity states, just like electromagnetic waves. But each helicity state looks just like one of these scalar fields in an expanding universe. So the magnitude of fluctuations in the metric should be the same as the magnitude of the fluctuation in other scalar fields up to constants, gravitational constants. And then it turns out that this is the strain parameter telling you what the relative change in lengths are, delta length over length, how big a gravitational wave produces as a change in length. It's proportional to this parameter, and it's scale independent. Inflation should produce a scale-independent spectrum of gravitational waves in the universe whose magnitude depends upon the energy density stored during inflation. That's an unambiguous prediction of inflation, independent of any of the details of, don't worry about that, that's just technical details, but it's a generic prediction of inflation. And it doesn't depend on the shape of the potential or anything else. So if we could measure gravitational waves from inflation, that would be an unambiguous test that inflation happened. And the intensity of the gravitational waves will depend upon the energy density stored during inflation, the scale of inflation. Okay. So this is a complicated picture from a Scientific American article I wrote a few years ago on this. And it's hard to understand, but I spent 10 hours with the artist, so you have to suffer through it. This is a brief history of time. This is looking at the universe, the first picture I showed you, the universe today. We go back in time, we get to the time where the cosmic microwave background was produced, when the universe was 300,000 years old. And then we go all the way back to the earliest moments of the Big Bang, when inflation happened. Now, inflation produces, we predict, gravitational waves of all frequencies with the same intensity. What will that produce in the universe today? So there are quantum fluctuations, they produce gravitational waves. But of course, let's take a gravitational wave with a frequency of 1 hertz. Okay? That wave does not start to vibrate until the universe is 1 second old. So you don't get those vibrations. But once the wave starts to vibrate, it redshifts as the universe expands. It gets stretched, and its intensity goes down. So what you have, let's say when the universe is 1 second old, you have this 1 second period gravitational wave starting to vibrate, but it gets damped out as the universe expands. Then you'll have gravitational waves of period 1 year. When the universe is 1 year old, they'll start to vibrate, but then they'll get damped out. Let's say 1,000 years, there'll be gravitational waves that'll damp out. But there will be gravitational waves of period 300,000 years. They will just begin to vibrate when this cosmic microwave background is formed. And what will they produce? They'll produce a polarization in that background. Because if I think of what produces the background, what produces the microwave background is, say this is an electron at that moment when the universe becomes neutral. It's about to be captured by hydrogen. It scatters radiation, and it scatters radiation uniformly. The radiation, if the radiation is uniform, it scatters that radiation to us, and then it gets captured. And that's the creation of the microwave background. The last electrons that are scattering radiation just before the universe becomes transparent. But if a gravitational wave the size of the visible universe comes by, then the universe will shrink in one direction and stretch in the other direction, at least from the reference frame of that electron. And that means that electron will see more intense radiation in this direction than that direction. And that will produce a polarization signal. If you think about it, if you work it out, if you have an electron and you have more intense radiation in one direction than another, and you work out the scattering, you'll find out that in the perpendicular direction, the radiation will be polarized. And it turns out you can work out the kinds of polarization that happen, and we label one kind E mode polarization, another kind B mode, to reflect the same kind of things we talk about as divergence and curl in electromagnetism. But it turns out gravitational waves produce a very specific type of polarization in the microwave background because they're quadrupole waves. That's all you need to know. So we can look for this kind of polarization in the microwave background as potentially a signal of gravitational waves of period 300,000 years that were generated at the beginning of time. It's not easy. Here's what, take a small region in that picture I showed you earlier, the hot spots and the cold spots. There are going to be random polarizations of the radiation. So this is what the universe would look like, what the signal would look like if there are no gravitational waves. And this is a signal with gravitational waves. It looks exactly the same. It's a signal that's 1 part in a million. It's damn hard to look for. Nevertheless, experiments like BICEP were designed to look for it. And BICEP did a simulation of what they might see looking at a small region in the microwave background, looking for these kind of snake-like patterns of polarization. This is what they said they might see if you had gravitational waves from inflation. In February 2014, they published this data. It was exactly what we predicted. Exactly. These are exactly the amplitude and the shape of gravitational waves that you would imagine in polarization produced by gravitational waves from the beginning of time. They claimed, we observed gravitational waves from a time when the universe was a millionth of a billionth of a billionth of a billionth second old. If this were true, this would be a direct measurement of what the universe looked like, of the physics of the universe at the beginning of time. Now, I say if it were true, and the reason you're probably not aware of it is because it probably isn't true. It may not be true. And the problem is this. This is another way of plotting the effect, what gravitational waves from the beginning of time would do to the microwave background. This is a multipole expansion. This is looking for the intensity of polarization as a function of angle on the sky. And this is the prediction of inflation. That's all you need to know. That's the prediction of inflation. This is the data they took. Look pretty good. Now, what are all these curves? These are noise, backgrounds. There are other backgrounds that will produce polarization. There's polarization in our galaxy. Radiation that's coming from our galaxy is polarized. And also, dust in our galaxy. If the dust particles are polarized, electromagnetically polarized, they're dipoles, then they'll scatter radiation and produce also polarized radiation. So this was the estimate of the dust in our galaxy, and it certainly didn't seem to get in the way of the signal. So this was from the BICEP detector. At the same time, the Planck detector, the satellite was up there, and it was also designed to look for polarization. Clearly, this would be a Nobel Prize, and the Planck people were very upset that they got scooped by the BICEP people. But they were very happy because BICEP looked at a small region of the sky, but Planck looks over the entire sky in many different frequencies, and they could measure dust. And they, within 2 months, produced a figure that said, okay, this part here is this. This is the prediction for inflation. And this is what they said could be due to dust in our galaxy. It turns out our galaxy is much dustier than we thought. And they said dust could produce a signal of the same intensity polarized dust in our galaxy could produce a signal of the same intensity as was seen there. Now, it doesn't have the curvature that you see here, but, you know, this could be just an accident of the eye. And they were very happy because they said maybe these people are wrong. Now, this is really a very important part of science, one of the reasons I love science. Because these people hated these people. And these people hated these people. So what did they do? They didn't cut each other's heads off. They said, let's do a joint analysis and find out what the right answer is. Because they didn't care who, and ultimately who was right. They cared what was right. And they did a joint analysis. Now, the two experiments look at different regions, so you couldn't do things exactly. But it turned out when you do a joint analysis, things are different. So let me just show you what. This was the original result that came from BICEP. It was some number that is 0 if there's no polarization, and it's non-zero if there's polarization due to inflation. And the number was very large. It was 0.2. And you could see that with high confidence, they claimed to observe gravitational waves from the beginning of time. This, and I'll go back for a second so you can see it, this was the new analysis. The likelihood, this is a likelihood plot, and so the likelihood is still maximum at some non-zero value of this quantity r, but it's not 0 at 0. And this is why this is physics and not medicine. Because what you can work out is that there's a 92% likelihood that the signal is non-zero, but 92% is not good enough if you're going to make a great discovery. In my field of particle physics, you need 5 sigma, 99.9999995%, okay? And so if you read the paper that came out in February of 2015, it says the final result is expressed as a likelihood curve yields an upper limit of r of 0.2 at 95% confidence. It peaks at 0.5, but disfavors 0 only by a factor of 2.5. This is expected by chance 8% of the time. So in 8% of the universes we live in, you'll see a signal like this just due to noise. And so if you followed this, the media said, oh, the signal's wrong. It's not clearly wrong. They may have seen something, but they haven't seen something at the level of confidence where you can claim a discovery. And we are building new polarization detectors at the South Pole that are more sensitive. And so we may know the answer in the next year or two. It may be that we can't get an answer. Because while we were lucky enough to be able to extract the galaxy from the temperature fluctuations, it could just simply be that the galaxy is so dusty, we can't extract the signal from the beginning of time for that. We may not be able to do it. But we're on the threshold where we may be able to do that, and some part of this signal may be right. And I just want to end this talk with some of the implications of if that signal is true, what it tells us. It's kind of remarkable. I was going to do one. One I will tell you, but I was going to show you the math, but I decided not to. One of the interesting things is that I talked about quantum fluctuations in space and time. We don't have a quantum theory of gravity. And some people have argued maybe gravity isn't a quantum theory. We have no evidence that gravity is a quantum theory. It turns out if you could measure these fluctuations, we'd be able to prove that gravity is a quantum theory. And it's a paper we wrote a few years ago. So it would be remarkable. The first thing we'd be able to say is that gravity is a quantum theory, and we need to find what that quantum theory is. We still don't know, but it would tell us that gravity is, that space and time themselves are quantum mechanical. They fluctuate quantum mechanically, which would be remarkable if you're interested in time. At some very small time scale, the Planck time becomes a stochastic quantum mechanical parameter. But the other thing is thinking about what happened here. Inflation happened because of some phase transition. When phase transitions happen in particle physics, the nature of forces change. That's what we mean. We know a phase transition happened, at least one in the early history of the universe, because we know that there are two forces that are very different now, electromagnetism and the weak force, which actually are unified into a single theory we now call the electroweak theory. And when the universe was a millionth of a second old, those two forces began to diverge because of a phase transition related to a field we call the Higgs field, which we discovered by looking for the particles associated with that field called Higgs particles. And CERN in 2012 discovered those particles. So we know that phase transition happened. But if inflation happened, it happened due to a phase transition much earlier. Why would we expect a phase transition to happen? Well, it turns out these are the three non-gravitational forces in nature, the strong force, the weak force, and the electromagnetic force. On scales we measure, they're very, very different. The strong force, which holds together quarks and protons, is very much stronger than the weak force, which is responsible for nuclear reactions and electromagnetism, the electromagnetic force. But it turns out, due to quantum mechanics, we can show that as you explore those forces on nature on smaller and smaller scales, the magnitude of those forces changes. And since, by the Heisenberg uncertainty principle, exploring things on smaller scales means using more energy to do it, if we think about it, as we explore systems with more and more energy, the magnitude of those forces changes. And it was known in the 1970s, it doesn't take a rocket scientist, to realize that the weak and electromagnetic forces get stronger on smaller scales, but the strong force gets weaker, and maybe they unify together at a certain scale. And that scale we called the grand unified scale. If they were unified, it was a scale 15 orders of magnitude higher in energy than the energy of a proton, or 15 orders of magnitude smaller in scale than the size of a proton. Well, it turns out that hope didn't work out. We can now measure these things exactly. If the only forces in nature and the only particles in nature are the ones we measure, it doesn't work. But it was soon realized that if in fact there was a new symmetry of nature, which we look in particle physics think of as being useful for other reasons, if that new symmetry came into play and new particles in nature came into operate at a scale around the scale where the Higgs particle exists, then the way those forces would change would be different. And lo and behold, they would unify at a single point at the scale. This represents a phase transition, because before that, all the forces in nature would be unified. Afterwards, they would diverge. This phase transition could be associated with the scale of inflation. That's why we think inflation may have happened. And the amazing thing is that if we measure gravitational waves from inflation, we will be able to probe the physics at this scale. Well, actually now 16 orders of magnitude higher in energy than the scale of the proton. 13 orders of magnitude higher in energy than we can explore at the Large Hadron Collider. We will never be able to create accelerators that can probe this energy directly. To create such an accelerator would require a radius of the Earth-Moon distance. That's not going to happen, given the economics of the world today. Not going to happen anyway. Now, we do build other devices to look for things that could happen at that scale, because, interestingly enough, to go back, if the three forces of nature unify at that scale, then it produces another interesting phenomenon. Diamonds are not forever. Protons will decay. All the matter in the universe will decay. Happily, for those of you who have diamonds, the lifetime of a proton we can calculate, and it's about 10 to the 33 years, which is 23 orders of magnitude longer than the current age of the universe, so you don't have to worry. How could we measure such a phenomenon if every proton lives 10 to the 33 years? Well, it's quantum mechanics, so it's probabilistic. If we could get 10 to the 33 protons in a room, one of them would decay each year. So he built a large detector. This is the largest detector. Where do you get 10 to the 33 protons? 50,000 tons of water. And in the Kamioka mine in Japan, there's an amazing machine where we, in a working mine, 50,000 tons of water with the laboratory cleanliness of a clean room put together with 11,000 phototubes waiting for a proton to decay. We haven't seen one decay yet in the last 20 years. Of course, remember what happened with the gravitational wave detector. If this machine goes offline for 1 second, and that's the second when it decays, then you have to wait again for another 10 or 20 years. So the fact we haven't seen anything, it doesn't indicate anything yet. If we measure inflation, if we measure gravitational waves from inflation, we will know the scale of inflation and we'll be able to predict how this could occur and help us build new detectors in the future. Alternatively, there is near here the most complicated machine humans have ever built, the Large Hadron Collider at CERN. If you go to Geneva, near here, if you take the TGV, you can see Geneva, and if you go out at the airport, you'll see beautiful farmland, but underneath the farmland is a 26-kilometer long tunnel with amazing detectors. No, I guess I didn't present detectors. I was going to, with amazing detectors inside of them. And the point is that the Large Hadron Collider detected the Higgs. But maybe it will detect supersymmetric particles. In fact, many of us thought it would detect supersymmetric particles before it detected the Higgs. It didn't. But it's still running, and it's going to run for 20 years. If it detects the supersymmetric particles, it will give us independent information about the possible existence of grand unification. So measuring gravitational waves from inflation will not only give us a picture of what the universe was like when it was a millionth of a billionth of a billionth of a billionth second old. And by the way, I would argue that is the greatest single development in the history of physics. Those of you who work on time frequency measurements know, I think, that if you can improve the precision accuracy of your experiments by a factor of 2, that's a big deal. By an order of magnitude, it'd be amazing. Right now, the earliest we can see into the universe is when it was 300,000 years old. If we measure gravitational waves from inflation, that will improve our measurement accuracy by a factor of 10 to the 49th. We will go back to measure from 300,000 years to a millionth of a billionth of a billionth of a billionth of a second. Never in the history of science have we taken a leap like that. It would be the most important leap in the history of physics. But there's a last thing I want to mention, and that is kind of remarkable. If inflation happens, it generically produces more than one universe. We now mean something different by universe than we used to mean. Used to, when I was a student, or maybe before when I was a student, when I was younger, the universe used to mean everything, whatever that was. Now we have a much more precise measurement, definition of universe. The universe is that region of space with which we could have once had causal contact or one day will have causal contact. Namely, it's that region of space that could, even over an infinite amount of time, communicate with one another. Okay, that's a reasonable definition of universe, because anything outside of that cannot impact physically on anything inside of that. Now, inflation causes the early space to expand exponentially. And what happens is, because of quantum fluctuations, some region leaves inflation here. It's like a seed forming, a snowflake forming. A phase transition happens here, and we get a hot Big Bang. But the rest of space is still expanding exponentially. And then later on, some other region may leave inflation, and some other region. But the space between those regions is expanding exponentially. And inflation, in fact, in general, is eternal. Space is generally, most of space is still expanding exponentially. We live in a region where a hot Big Bang happened. And if that's the case, then we live in a multiverse, not a universe. We live in a space in which there are many different universes. And interestingly, when you leave inflation, the physics that results after inflation can depend upon how you leave inflation. Just like if you have ice crystals on a window pane in the morning, they can point in many different directions randomly, depending upon how the phase transition happens. When you leave inflation, the laws of physics after inflation ends, the forces can be different. And that means in each universe, the laws of physics can be different. This is sort of an artist's rendering of what you would expect. This is sort of inflation, the regions of space happening, expanding. In between them, there's some universes forming. And in some universes, the laws of physics are such that galaxies form. In other universes, the laws of physics are such that no galaxies form. And if that's the case, we may understand why the parameters of the universe are the way they are. And it's kind of it's a disappointing result if it's true. It means that the universe is the way it is because there are astronomers here to measure it. Not because it was designed for astronomers, but it's kind of cosmic natural selection. We would be amazed to find ourselves living in a universe in which we couldn't live. That would be worth a book, but no one would be around to read it. So this is I wrote about this years ago, and we've been speculating that maybe many aspects of our universe are so-called anthropic. Maybe certain parameters of our universe are just an accident. Now, this is speculative, and it almost sounds religious, and people have argued, well, it's not physics, it's metaphysics. That's true. But the important thing is, if we can measure gravitational waves from inflation, we will be able to check the model of inflation. We will be able to probe the physics that produced our universe, and we'll be able to discover empirically if that model produces an eternally expanding universe elsewhere. So even though we won't be able to measure these other universes directly, we will have a model that describes the three forces of nature, other than gravity, that may make 51 predictions, and the 52nd prediction is that there's a multiverse. We can check all the other 51 predictions, and if they agree with observations, we pretty well are confident that the 52nd prediction is correct. It's the same as 1905, when we first predicted the existence of atoms, when Einstein did his calculations, PhD thesis calculations. No one thought we'd measure atoms. No one imagined we'd ever see atoms. We all knew they existed. If we can measure gravitational waves from the beginning of time, we will not only learn about the beginning of our universe, but the beginning of many universes. And I find that remarkable. We are living in a remarkable time. Going back to the original picture, this is the universe we see. It is amazing to be living at a time where not only that we can see this image, but we're on the threshold, potentially, of going back and observing the universe at its very beginning, the beginning of time. It's an exciting time. Thank you very much.
So we'll take time for a few questions. And it's hard to see you guys, if there are any. Professor Handel?
I would like to point out that here in this community, every time somebody makes a 1/f noise measurement, he does in fact perform a macroscopic quantum interference process. He actually, we have been doing that the community since 1925, since people learned to amplify signals, and it is present, for instance, in a quartz crystal. When the elementary act of dissipation happens and one phonon is lost from the main resonator mode, then two copies are formed. Actually, an infinity of copies are formed. The one that's the crystal, and the other one is everything that's obtained with Bremsstrahlung associating the loss of that phonon. And these two interfere and they give the observed one, as people here in the room have demonstrated for the first time. I'm talking about the professors at Franche-Comté University. I'm talking about, for instance, Fabrice Stahl. I'm talking about Bourquin, Sibyl, professors from Paris. 8 of them in a collaboration of 5 years have proven this, standing on the shoulders of Fred Waltz from NIST, of Van der Zeel.
Okay, thanks very much. I didn't really hear a question there, but...
Yeah, well, I'll take it as a comment, but usually comments are longer than questions. But look, the work that's being done in many areas here and elsewhere on measuring macroscopic quantum mechanics is remarkable. And as our precision increases, we'll be able to do even more interesting measurements. So in no sense was I arguing that this was the first example of the measurement of macroscopic quantum mechanics. I was arguing that it may be surprising to people that the universe itself and in fact everything we see in the universe is an explicit example of macroscopic quantum mechanics. And so to the extent that we can measure in the laboratory, we have greater confidence that our application to the universe works. Are there any other questions? Oh, okay.
James Camparo.
So I've wondered about this for a long time. People talk about quantizing gravity, and so that's quantizing the metric. But the metric comes from the field equations, and so the metric is defined by mass, energy, density. All right, because maybe that's where I'm getting confused. But so couldn't it be that the metric is classical, but it takes on quantum appearance because it's being generated by quantum mechanical matter?
Okay, Einstein's equations equate the metric, not really the metric, but something related to the metric, a curvature tensor, to the energy momentum tensor of matter. Okay, and what you're talking about is something called semi-classical gravity, where you have classical gravity which interacts with quantum material. And we actually could do calculations in that domain very well. And we predict, for example, that black holes radiate. Hawking's prediction that black holes radiate. It takes gravity as a classical phenomena and interacts it with quantum matter. But empty space, devoid of matter and radiation in general relativity, the metric of flat space, if gravity itself is quantized, will fluctuate, even in the absence of matter and radiation. If the metric itself, the metric is a quantum mechanical parameter, it will fluctuate. And so that is quantum gravity. The problem is that when we try and turn general relativity into quantum theory, we take pure gravity, no matter, no radiation, just pure gravity, namely the metric. We get infinities. We can't do it. We don't know what the results are. And that's the quantum theory we'd like to figure out, and we develop string theory and other candidates. We don't know what the answer is. But the metric itself, if gravity is a quantum theory, the metric itself will fluctuate independent of the presence of matter and radiation. And what is exciting to me is that, and I could have shown you in 2 slides, but we've shown that if the metric does not fluctuate independent of matter and radiation, then you will not generate gravitational waves during inflation. And that's what I find very exciting. Because, and the reason, and maybe I'll end with this, but it's kind of interesting. You probably heard of Freeman Dyson. You know who he is. Freeman is a contrarian, and a lovely contrarian sometimes. And he's written a beautiful paper that shows there's no way we can measure that on Earth that gravity is a quantum theory. To do that, you'd have to measure individual gravitons. If gravity is a quantum theory, then gravitational waves are composed of particles, like electromagnetic waves are composed of photons, gravitons. But you could look for a graviton detector by making a very sensitive version of LIGO, sensitive to a single graviton, just like you can detect individual photons. He's shown that if you built a detector like that on Earth, it would collapse to form a black hole before you could make the observation. You can never do it. So he's argued maybe gravity is a quantum theory. And what I find very exciting is the universe is a graviton detector. The universe allows us to do what you can't do causally. And I find that remarkable. I mean, I actually came up with this when I was listening to Freeman talk about how impossible it was to measure it on Earth. So if we can measure gravitational waves from inflation, we will have a graviton detector, and we'll know that gravity is a quantum theory. And so that would be, from my mind, a very important, because empirically we don't know. We all think gravity is a quantum theory, at least most of us do, but we don't know for sure. Maybe that's a good way to end, or?
Yeah, I think so. We're running a little bit late, so let's thank Lawrence Krauss again, please.